Hi, Algebra 2 students. This week we're going to wrap up our discussions of absolute value functions by transforming them. As I had said earlier, we will transform every function we learn about this year. So this is the first of many. We will keep coming back to these rules over and over again, and a little bit of it should look familiar from a few weeks ago. Before we start transforming these functions, though, let's take a look at our parent function and pay attention to some important details about it. I'm going to start by looking at the graph. I want you to notice on the graph that the origin is at 0, 0, and the next point is at 1, 1. The absolute value function has a slope of 1 that makes a V shape. Knowing that it goes through those 2 points of 0, 0 and 1, 1 is very important when you're trying to look for stretches and compressions, as well as any kind of translation of your graph. Another thing to pay attention to is the domain and range. Remember, domain are your x values, range are the y values. The domain is all real numbers. You can put any value in for x. However, your output, your range, are all the non-negative real numbers because the absolute value function is always positive. All right, let's start looking at our first two transformation rules. First thing we're going to look at are translations. Vertical translations happen when we add or subtract to the end of the function. When we subtract, when that k value is less than 0, that means we are moving down. When we add, that means that we are moving up. So let's take a look at these three examples. First thing I'm going to put on my graph is the parent function. F of x is equal to x. Again, it goes through 0, 0 and has a slope of 1. Now if I look at the next one, this one is absolute value of x plus 3. We said that if we see a plus something at the end, it goes up. So every point on this graph is going to move up 3 points. So our vertex moves up 3 points, and everything else moves up 3 points. It remains a slope of 1 on either side. Last one, absolute value of x minus 2. So instead of starting at 0, 0, this time we'll go down 2, and our graph will start at negative 2 and keep that slope of 1. Let's look at horizontal translations next. Horizontal translations occur inside the function. Turn that off so I don't get that message again. Okay. So, horizontal is our x value, right? Our horizontal axis is the x-axis, and x is the input. It happens inside the function. So we will see all of our horizontal transformations happen inside of the function. Okay, look at our formula for horizontal translations. We can see it's x minus h. Notice that minus h. The shift is going to be the opposite of what you are expecting it to be, okay, because it has that negative there, that opposite there. Let's look at that more carefully with these couple examples. We know what our parent function looks like, so let's just focus on our first transformation. X minus 3. So remember, x minus h. The h in this case is a positive 3. So this is a horizontal translation, right 3. So rather than going through 0, 0, it's going to move to the right 3 and then make that V shape. The next one, again, x minus h. Well, I see a plus there. What kind of subtraction problems end up becoming addition? That's right, minus a negative. So what we see here is this is actually a -2. This is a horizontal shift left 2. You see what I mean? How it's the opposite of what you think it's going to be? So let's sketch this one out and talk a little bit more as to why that is. Okay, so before I switch screens, I'm going to write a little more clear on here. So this one is left 2, and the other one I think I used green for. This one was right 3. All right, so let's look at a graph to help us out. So here I have in purple the absolute value parent function, and in orange I have a translation left 3. You can see it in the graph, and then you can see the left 3 here because I have minus and -3 inside of my brackets, which is equivalent to a +3. So think about this. Every point here has been shifted to the left 3. You can see that in the horizontal change in the number. The 5 turned to a 2. It was subtracted 3. But in order for us to change the input so that the output remains the same, stays at that level 5, notice 2 plus 3 is 5. If I switch to a point down here, if I label this point right here, it's over 2, up 2. It got shifted over there, and this point is -1, 2. Oops, I forgot my negative there. How do I take a -1 and turn it into a 2? I add 3. So we have to remember the reason that these rules seem a little bit almost opposite for any type of horizontal transformation is because we're changing the input, but we want the effect to take place on the output. And so in order to balance that out, we have to use kind of an opposite here. Let's look at a few more examples. Okay, as we look at these examples, notice that this -h is our horizontal shift. That +k is the vertical shift. And so if we have a function that just takes on this form, there's no stretching, there's no compressing, there's no negatives that make it a reflection. All that's changed is its location. So we can identify its vertex by looking at those 2 values and identify the vertex of the graph very quickly. All right, it says perform each transformation on f of x equals the absolute value of x, then graph the transformed function. All right, so it says 5 units down. Well, remember vertical translations, we add at the end. So if I want to go 5 units down, I need to now subtract 5 at the end of my function. I can graph this in Desmos or my graphing calculator to double check my answer, but I know I did this correctly. So I'm just going to go ahead and sketch my graph that's down 5 and then show my absolute value graph from there. All right, next one, we're going to go 1 unit left. Left and right is horizontal. That means we subtract h. So 1 unit left is like a -1. So my h is -1, and minus a negative actually means to add. So this is what my function will look like. When we write these new functions, we should actually be using g of x equals. And to graph the parent function that has moved 1 unit to the left, we just go 1 unit left of the origin and draw our function from there. When you're working on your homework on your own, I highly recommend that you flip over to Desmos and type in whatever it is here that you wrote and get that visual. You know what 1 to the left looks like. So if it didn't move 1 to the left, you know you made a mistake. So use that graphing calculator technology to help you. All right, a couple more, and then we'll take a break before we move on to reflections, stretching, and compressing. All right, we're going to translate our parent function this time so that the vertex is at -1, -3. So let's write down what that means. If the vertex is at -1, it moved left 1. And if it's at -3, then it went down 3. So f of x equals x minus h plus k. Oops, you can't see that. All right, my h is -1. My k is -3. But remember, a negative, or subtracting a negative, actually means to add. So my new function will be the absolute value of x plus 1 minus 3. We'll draw a sketch of this graph. It would be left 1, down 3, kind of running out of space, right down there. One more. We're going to translate our parent function this time so that the vertex is at 4, -2. So that means right 4, down 2. That's what we should expect to see when we're done. Let's write out our format. X minus h plus k. 4 is our horizontal shift. -2 is our vertical shift. Our g of x is equal to absolute value of x minus 4 minus 2. And what our graph should look like is it should go right 4, down 2, and have its vertex right there instead of at 0, 0. All right, that is it for translations. We'll take a pause, and then the next video will have reflections and stretching and compressing.